Welcome back, everyone. I hope you had a lovely lunch. We're going to move on to our next session, best practices in passive house MURB ventilation systems. Here we have today with us Josh Lewis from Nerva Energy, based right here in Hamilton. So we look forward to your great presentation. We will be taking questions after the presentation. We'll have a mic to go around the room, and then, of course, if you're online with us, welcome, and please put your questions in the chat. Let's now hand it over to Josh. Please give a round of applause for him.
Good afternoon, everybody. Hope lunch wasn't too filling, and let's see if we can make this interesting and learn a few things. So we always got to start off with why we're here, right? So, I mean, there's definitely, we know that ventilation systems in any building are critical for energy performance, but also maintaining a high level of indoor air quality. And, you know, indoor air quality, I'll be honest, as an energy efficiency guy, I didn't know or even think about IAQ much before COVID. That conversation has now changed. I hope it's changed the entire industry for now and forever. But certainly in passive house buildings, you know, we have to be ultra concerned about this because of the lack of significant infiltration across the envelope, right? Now, it's not that mechanical engineers counted on infiltration across the envelope. They were not allowed to do that. But we know, you know, old leaky buildings. I live in a house that was built in 1895. I know it's a sieve, right? But, you know, the reality of it is that in passive house, because of that air tightness of the envelope, ventilation becomes much more required. And, you know, here's the first example. I found, I don't know the name of this building, but that's a pretty cool looking passive house building, apparently in Spain, multi-unit residential. Very interesting offset windows there. So what are we going to talk about today? I'm going to lay it out pretty much like this. We're going to start with a little bit of refreshment on indoor air quality, something I spoke a lot about during the pandemic, kind of the intersection between that and energy efficiency. We're going to look at the history of ventilation systems in apartment buildings. What are the different types of ERV systems? How do their performances kind of vary? The ductwork configurations we're typically seeing in passive house designs here. You know, and then talking about ductwork leakage and how it can be addressed, a real hidden problem that can really impact your system. And then a couple of kind of future thinking items that you can look for future improvement. So let's start with IAQ, right? Indoor air is almost always more polluted than outdoor air. That's not a fact I think a lot of people would recognize, but, you know, unless we live in a place like, you know, and I know in China and India, they have some very large outdoor air quality issues with smog and particulate. But here in North America, we're pretty fortunate to avoid most of that. So typically our indoor air is much more polluted than our outdoor air. And I think this really, again, raised kind of the level during the pandemic, and everybody was kind of focused on, you know, this, you know, transmission of this extremely airborne virus. But, I mean, there's all kinds of different things we contribute to bad indoor air quality, right? Well, obviously, we've got particulate matter, PM5, PM10 measurements, but formaldehyde from building materials, you know, there's a lot of things within, you know, well and lead that, you know, try to get you away from, you know, products that emit VOCs in your buildings. Certainly, you know, household odors and gases, gas stoves have become like the new issue. Certainly a good idea to get rid of gas stoves for carbon, but also for indoor air quality. Ozone is a problem. A lot of that is generated in cities, especially due to vehicle exhaust. And then carbon dioxide. I don't know if anybody brought an indoor air quality monitor with them in their pocket, but if they did, I'd love to see what some of your readings are around here. But yeah, CO2 can build up in rooms like this if they're not properly ventilated, and that can impact everybody. So, you know, these are the things we generally have to be aware about. But if we look at, you know, high performance buildings, high performance envelopes, you know, they share a lot of these common metrics, right? You know, we've all heard a lot this week about continuous insulation, certainly high performance components like triple pane gas filled windows. We know our building envelopes have to be airtight. Shading and solar design is a key element, as well as thermal bridge free construction as much as possible. But all of that also has to be, you know, we have to think about the ventilation along with that. So I don't take credit for this graphic. Somebody else a lot smarter than me put this together, but they clearly understood the power of ventilation and the power of energy recovery ventilation in order to hit our targets when it comes to the mechanical systems in passive house or other types of high performance buildings. So ventilation design is a key part of the whole building performance, right? We've heard a lot about the envelope, but the ventilation design is just as critical to hitting the passive house metrics. So when I talk about indoor air quality, I kind of break it down into 4 categories. Filtration, we need to filter the air that's coming into the building, the air that we're recirculating in the building. Pure humidity. Humidity control is very important. I got a quick slide on that in a minute. Dilution is a combination of moving the air through the building, but also bringing in the proper amount of outdoor air to dilute at the same time. So it's moving and diluting the air. And then purification is kind of that 4th rung. That's a technology that I'm not going to really spend any time talking about today, but there are ionic-based generation technologies out there that are proven to improve indoor air quality and kill COVID-19. But there's a lot of there was a real infodemic in that space during the pandemic. Everybody had this magic product that would generate ions that would clean the air. So if you're ever going to look in that technology, be very careful. But there are a few proven sources out there. Back to humidity, actually, I think this is something that we miss a lot of times in our buildings. So the proper optimum zone of humidity inside any building under any conditions is between 40 to 60% RH. And the reason is this graph. And this is based on decades and decades of research by some very, very smart people. So, this is something I think we do, at least here in Ontario, we do a pretty good job of in the summertime, because a lot of our air conditioning load here is latent, not sensible load. So we're having to remove humidity from the air before we bring it in the building and keeping those RHs down. Where we do a terrible job of this is in the winter. I have seen a conventional multi-residential building that had a humidity level in the hallway in the winter of 7% RH. And, we shouldn't expect anything different, because it has a traditional makeup air, which is taking dry, cold outdoor air, heating it up, reducing the humidity even further, and then dumping it in the corridors. So like 7% relative humidity, you might as well be in the middle of the desert at that point. Not a really good thing for indoor air quality, but certainly not the core focus of today. Now, I'd like to think that when it comes to ventilation, we can take some guidance from the hospital, the hospital sector, right? There are no better ventilated buildings in our common building stock than hospitals. And they're confined by codes to, have consistent airflows, constant volume systems. The pressurization between zones has to be maintained so you don't get contaminants flowing the wrong direction. There's a lot of things, but we can't build all buildings like hospitals. We can't ventilate them all like hospitals, or otherwise our energy budgets and even our construction budgets would be out of whack. But I think there's some things that, we can learn from that sector and bring over into the passive house world in order to make our buildings better and as healthy as reasonably possible, but not going necessarily to that extra healthy step that hospitals are mandated to do. And I mean, what happens when you don't have ventilation? So this is actually a study. This is a picture from a study from one of the earliest COVID outbreaks in China. So this was before we even went into lockdown. This is late January 2020. And what happened was in this restaurant is a patient 0 walked in. As you can see him, Mark, he sat down to have dinner. And that AC unit on the wall actually drew air around the room in a very specific pattern and infected all those other people in red, because it was pushing air down one side and pulling it back. But notice that nobody in the other set of tables closer to the bottom of the screen got infected that night, because they weren't in that airflow path. But guess what? That's just a split system AC unit. There's no outdoor air associated with that unit, right? It's just a head that was cooling the indoor air, 100% recirculation, and probably minimal, if not zero, filtration on it, right? And if there was anything on it, it was probably just a dust screen. So, when we don't ventilate properly, this is what can happen. There's even some studies going on now in some buildings in Hong Kong that suggest that COVID was carried upwards in multi-residential buildings due to stack effect. That it literally came up, and it's not just one building. There's multiple buildings that they found this on. They found COVID traces 3 stories above of an infected unit in an empty unit, but like that had traveled upward and infected people along the way. So, a lot of things to think about, and a lot of ways we can make our buildings better. So, just some takeaways on indoor air quality, right? When it comes to filtration, we always want to see at least minimum MURB 13 filters on any system these days that has recirculated air. You can get away with MURB 8 on outdoor air, but I would still suggest 13 to be honest. Dilution, we need to see this constant air circulation with the appropriate amount of fresh air exchange, whether that's a fixed amount of fresh air, whether that's CO2 demand control ventilation driven, however way you're going to guarantee that. Humidity, certainly keeping in the 40 to 60% range. In cold climates, you're generally going to need a humidity injection system, which is, typically a feature of buildings that we've only seen on Class A office buildings in the past, would have these humidification systems on their main air handlers. But smaller buildings, rooftop buildings, even MURBs, I've rarely ever seen a MURB that had any kind of humidity injection in their makeup air for the wintertime. That's a miss. That's a huge miss. And I know it adds cost, it adds water usage, it adds energy usage. But you can't put a price on health and safety. It's just impossible to do that. And certainly purification, it is becoming a more common feature. I think the technologies the pandemic has really allowed these ionic technologies to really show their effectiveness or lack thereof. So be diligent, but certainly the technology's out there. Okay, so let's start talking about MURBs. So here's your typical multi-resident, unit residential building, which, we think is pretty simple as far as building styles go. They're a square, rectangular box and, pretty consistent floor to floor. But there's a lot of things going on with the airflow in these buildings, right? I mean, we have the natural impact of air pressure, the wind pressure hitting the building, and that's, impacting the airflows. And then, of course, we have the stack effect, right? Warm air rises. The taller the building gets, the worse this impact is. And it's, it's physics. We can't get away from it, but there are ways to mitigate it. Then we have some mechanical effects, like the air leakage in and out through the elevators and stairwell shafts. Unfortunately, those shafts have to be continuous, which isn't great for stack effect, but they're stairwells and elevators. There's no other way to do that we know of. We also have, of course, the ventilation in, or the mechanical plus the pressure. So that's the red, that's the makeup air system on this traditionally ventilated building. We've got occupant impacts. Occupants can open and close their windows whenever they feel like it, right? That's their choice. So we've got that impacting the flows through the building. Of course, we've got exhaust in the building. This particular diagram is showing more of a in-suite exhaust direct to the outdoors, but that's something that comes on and off during the day. Of course, envelope leakage. Don't need to talk about that. Passive house going to be minimal. Traditional buildings probably much larger. And then we've also got interior air leakage between the suites and the common areas and the floors, right? In the perfect world, every suite would be an airtight box. But the reality of it is in older buildings, they're not constructed that way. So we have that to deal with as well. So this is a little bit harder problem when you start to do this. There is no perfect state. There is no steady state. There's only systems that are passive or active that try to balance each other out and kind of work through the whole seasonality together. So corridor ventilation. This is how, we've traditionally ventilated multi-unit residential buildings. We pressurize the corridor, usually a minimum of 60 CFM a door. I've seen way more. I've seen a little bit less. But we're delivering that air traditionally through those undercuts in the suite doors, right? So the one benefit of that type of system was they were obviously inexpensive to construct, right? And that's why we built them for 50, 60 years. But they're just not acceptable anymore, right? There's no heat recovery, so there's not efficient. You can't build that building anymore in Toronto or under the BC step code because it just doesn't pass the energy modeling, hasn't for a while. And it's impossible to guarantee consistent airflow to every suite. You got balancing issues, you got stack effect issues, you've got ductwork leakage issues, and all of that just ends up being negatively impacted the IAQ of the building. And ultimately, if you're delivering the air undercutting the door, you have unsealed doors, right? So you've got smells, noise, pests, even potentially security risks. Because now you've got this, non-sealed door that's got an inch of gap or something like that underneath it that, that can introduce irritants into the suite or irritants out of the suite into the corridor. So obsolete, yes. Are we going to have to retrofit these? Yes, we are. Now, there's also two traditional ways. That was traditional supply ventilation, but we also have two traditional ways that exhaust ventilation was done. One was the through wall exhaust. So this is where in a multi-res building, every suite had two, one or, usually two small exhaust fans, one for the range hood, one for the bathroom, pulling the air out and going directly outside the wall. Certainly guarantees airflow. I mean, if the fan's running and, and it's clean, then you're getting the air out. And any failures on that type of exhaust system are contained to that individual bathroom or that individual range hood. But, certainly adds to the in-suite maintenance requirements, which is, not a good thing, especially in rentals. It's more noise than, say, a centralized system. The heat recovery in these types of systems is pretty disruptive to retrofit. I mean, it can be done, but you're going to have to put an ERV in suite, and you're going to have to make some major ductwork and bulkhead changes in order to kind of retrofit that in. It's possible, but it's difficult. And certainly a negative impact on whole building airtightness because, like the bottom picture shows, you now have one or more penetrations from that suite to the outside. And what Passive House teaches is we want to get to as minimal penetrations as possible through the building envelope because it'll just make the building more airtight. Now, the other way is central exhaust. And this is actually also a traditional design. I've looked at many, many buildings in this area, and there's no rhyme or reason. Some are suite exhausted, some are centrally exhausted. But this is where we're pulling that air from the suite washrooms and the kitchens to the roof. The benefits here is heat recovery can be easily retrofitted. The maintenance is contained on the roof. But again, it's still impossible in these systems traditionally to guarantee enough exhaust airflow to every suite because you're still dealing with the balancing, the stack effect, the ductwork leakage, and inefficiently or quite to my surprise, to be perfectly honest, heat recovery was not traditionally done on these types of systems. So that meant that these types of buildings, as we stand here today, the room temperature air is leaving those buildings 24/7, 365. And here's a great example of that from a nice shot high above Toronto, looking back towards the downtown core, right? So we got supply here, we got exhaust here, and yeah, where's the heat recovery? Like, talk about a missed opportunity, right? And this is not just one building. This is hundreds of buildings that are just screaming for a retrofit on the roof. You could replace all those fans, supply and exhaust, with one heat recovery unit on this side of the building. And by the way, now you'd actually heat the corridors because there is no heating in that supply air right now. So they're literally pumping cold air into the building while they're exhausting warm air out the top within 3 feet of each other. Crazy when you think about it, but there's going to be a lot of those going on because that is a key decarbonization plan for those types of buildings with that existing infrastructure. Now, we have moved on a bit. So really, the newer design is the in-suite ERVs. This is where the suites are self-contained, self-pressurized. These ERVs are always on. Sometimes they also have a boost mode as well when you take a shower. So the corridor ventilation is reduced because the suites are no longer receiving air from the corridor. The doors of the suites are sealed. So you definitely get improved energy efficiency. We finally got some heat recovery here. The suites are self-contained, so that produces a better product. It's more comfortable. I'm now getting closer to my airtight box, but still has issues. Greatest in-suite maintenance requirements, because now you don't just have necessarily a fan coil or a heat pump unit. You've also got an ERV that's got to be maintained. Again, a problem in rentals, a problem in social housing, but I would argue probably also a problem even in the condos because the owners are not necessarily that savvy and they don't realize that these need to be maintained and maintain the whole performance of the building. But you're putting it on the owners. In a rental building, the tenants are never going to do it. You're going to have to do it as a maintenance program for the whole building. But these also have a very negative impact on whole building airtightness. And I'll talk about that more in the next section because of the multiple penetrations. And ultimately, you're never going to get to the highest levels of efficiencies with these units. I truly, truly believe that. And it's actually been reinforced this week. Of all the passive houses that I see have been delivered or are coming, most of them are going to centralized systems. And I think there's some really good reasons for that we're going to explore. So this certainly is the newest design. The suites are serviced by shared ERVs that are always on. The corridor ventilation is again to reduce. The suite doors are still sealed because these are fully ducted systems, which we'll get into more detail on that. So from what I know, these are the highest level of efficiency. So these, I would call, the suites are centrally serviced, but yet still individually pressurized. So you get the best of both worlds here. So now your in-suite maintenance requirements for at least the ventilation just went to zero. There's nothing in the suite. You get a large positive impact on whole building air tightness because the number of penetrations just drops like a rock. And, you know, again, likely about the highest efficiency possible that you could expect. So what does the Toronto Green Standard tell us? So first of all, it tells us that we're going to passive house, right? And I won't take credit for that graphic. That is literally from the city of Toronto, right? So by 2028, we're building nothing in Toronto for large buildings but passive house level buildings. They don't have to be certified necessarily, but they have to hit that TEDI. So first of all, you know, these guys, you know, Toronto's pretty smart. They know that the infiltration has to get better. Code 25, you know, minus 25% airtight, minus 50, minus 75. Building envelope air tightness has to improve. I think we all know that. But also ERVs. I mean, ERVs are standard today. There's no way you're hitting a TEDI of 70 without them. But it's ERVs plus. Like we got to take these systems to their maximum limit in order to get to that level. And again, we've already seen that in the passive house world. And, you know, the corridor ventilation, you know, kind of the standard today for delivering air just for the corridors is about 30 CFM a door. That's about where a lot of engineers are in terms of carefully shrinking their numbers. But reality, we have to get to 15 down to non-pressurized corridors. Now that scares a lot of people. A few years back, that not pressurized was about 7 CFM per door, but it's since been revised down to literally not positively pressurized corridors. So, you know, that is where we need to get to hit these energy targets, right? And a lot of that impact is whole building air tightness, whole building envelope air tightness will help us get there. But we do have quite a bit of a challenge ahead of us. So just some takeaways on this section, right? I think we all understand now that, you know, the airflows in MURBs are very dynamic. Corridor ventilation is obviously obsolete. Through wall exhaust, obsolete. Energy recovery is required, you know, under any standard pretty much these days. The centralized systems do have some significant benefits, and the corridor ventilation rates, you know, we got to get them down. If not pressurized, not positively pressurized, then down to, you know, about 7 CFM per door, which is kind of where ASHRAE actually says is kind of the bottom limit for that in the corridors. So let's look at ERV systems. So your typical in-suite ERV, you can, you know, there's either standalone or integrated. You kind of see a mix of both these days. Sometimes, you know, the fan coil heat pump unit has this integrated ERV. Other times they're built into a separate bulkhead. I would argue that the integrated ones are a little harder to set up. Maybe not quite at the level of performance, but certainly check your data sheets. But in any case, these are coming in at about 55 to 75% efficient on the recovery. They do require at least two exterior penetrations, but again, they're maintenance heavy because now you have this, you know, filters, the energy recovery core. There's another fan in the suite that's, you know, separate from the fan coil or the heat pump fan to move the air through. So there's, you know, there's a lot to think about when you're putting these units in, and, you know, what the tenant's going to be, how these are going to be maintained. So in a typical in-suite system, you know, we have the supply and we have the exhaust. Okay. So in this case, the exhaust is pulling from the primary bathroom. So there's the ERV system ductwork all in the red there. So really just servicing one bathroom from an exhaust perspective. The supply air is just being dumped back into the suite or into the fan coil return just to get that fresh air in there. But that's just part of the ventilation of this suite. We also have here, there's the two exterior penetrations, first of all, for the ERV system. And then we have two direct exhausts. Now this is a corner suite, as you made a guess, a corner suite on the building. So it's got wall on both, outside wall on both sides there. But, you know, we end up with two more exterior penetrations for the range and the second bathroom, and potentially a dryer is also a common second one, because you can't put those types of exhausts through an in-suite ERV. It would just gum them up. So, you know, what we ended up here was, you know, this type of design, why code compliant in Toronto today is not really where we're looking to get to or where we need to end up, because we got too many penetrations, you know, too many loads that are directly exhausted. This will not be standard going forward. It just can't be. Now, there are some options to start to get rid of some of these direct exhaust paths that apply to both the in-suite or even the centralized systems. Recirculating range hoods. You can do these in MURBs. The only caveat is there has to be some kind of general exhaust in the kitchen. So you can have your recirc range hood, but like up here on the bulkhead, there's got to be an exhaust, right? Constantly pulling exhaust. You don't necessarily need to directly vent the range hoods out. The other thing is heat pump or ventless dryers. These are common. You can go to Best Buy and buy these. There are major developers in the Toronto area that have been putting these in suites in years. They're heat pump dryers. They're more energy efficient. They cost more, but they also don't need a vent. So you start to put some of these things start to think in here. You start to, okay, I can start to get rid of some of that direct exhaust. I can start to get rid of some of these penetrations, and these are some strategies that people are already using. But when we look at the design, right, we back to the in-suite ERVs. And then we start to look at the central systems, which kind of is where the passive house world is today, right? So these centralized systems are 90% plus efficient. And that's not paper efficiency. That's like real efficiency, because they are using these heat cores that are literally just metal blocks. So they're very easy to clean. They're very easy to maintain. They're not even made of special material. Admittedly, they're heavy. Those types of central systems are very heavy. They have to be structurally reinforced underneath, but it's where the passive house world is, and I think will continue to stay. Plus, the maintenance is a lot easier, not just because the cores are pure metal, but because now you have one place to do the maintenance on the roof and not in every suite. So what do centralized systems look like? There's kind of two major ways that I'm seeing these being done in the market. The first one is the easier one to get your head around, is what I call a hallway ducted design. So you can see here, there's supply and exhaust ducts, which are run vertically in really the space that your traditional makeup air shaft would be, but instead of just being one shaft, it's two shafts or two ducts within a shaft to supply exhaust and exhaust air. You then run the ductwork in the ceiling of the corridor. So what's important to think about that, though, is you need enough ceiling height, minimum 9 feet, right? If you got 8-foot ceilings, you're not going to have enough space to contain that ductwork in the upper part of that hallway ceiling. So now you're looking at an architectural decision where you have to commit to 9-foot ceilings in the corridors. And then you can see there's 2 fire dampers per suite, mandatory to isolate the suite from producing any smoke that could flow back in the system. And then you got the ductwork branching off in the ceiling to each suite through penetrations, but that's obviously all hidden and typically in some kind of drop ceiling or some kind of ceiling that can be opened up for maintenance. So that's a one way places are going. And what that looks like from a vertical perspective is, you got your central ERV on the roof, and it can be multiple units for the building depending how big it is. You got the vertical run, and then you've got the branches on each hallway to duct out horizontally down the hallway and then to penetrate into each suite. I think that's, pretty straightforward. But there's also, interestingly, what's called a suite riser design. So this passive house building, and both of these, by the way, that I'm showing you here are passive house buildings. This one for every 2 suites, there's one shared ERV riser. And I'm going to zoom in here on the next slide so you see what that looks like. So in this case, they decided to put those vertical supply and exhaust shafts in the demising wall between the 2 units. I don't have any insight as to necessarily what drove this design over the hallway ducted design. Maybe they didn't have the ceiling height in the hallways. I can only speculate. I've certainly shown this before especially to architects, and they kind of grimace a little bit because they looks like these 2 ducts are like wider than the demising wall, and in a sense they kind of are. But they were able to design these suites to hide those, or they're certainly not visible in any sort of way. So, and then there's still the fire dampers, 2 per suite, because you got to be able to isolate the system. And then you see the in-suite ductwork. There's the supply, there's the exhaust, and there's the fan coil, the VRF, which ties that all together to get that ventilation throughout the suite. And what that looks like from a vertical perspective is this. So you see all the ERVs there green on the roof. Those are all the suite ERVs, each one doing 2 suites per floor. And then you got a common corridor ERV in the middle there, which is doing the hallways. Now, this is the roof layout also for that suite riser design. So you see the common corridor ERV, you see the suite ERVs in green, and then you see the VRF condensers. This happened to be an air source VRF building. The one caveat I'll say about this is that I really believe I would have not done 8 in-suite ERVs. You could have done that instead of 8 green dots. You could have done that with 3 and tied the ductwork together for the left and the right side of the building into larger units on the roof. So I would have done less equipment. I think it would have ended up with a few more larger systems, a bit more ductwork. I think it would have been cheaper though, and probably less time to maintain overall in the end anyway. So that would be my only comment about this. But other than that, a good design, if you can get your head around, putting that ductwork into the demising wall in between each pair of suites. So just certainly options out there for how to do these in real buildings that are really operating. Now, we also have to be aware, though, of some of the limitations of certain ERV technologies. I mean, I've talked about the in-suite. I've talked about the centralized unit, which, the best units have heat cores. But there are other types of centralized units. There's units that have more of a heat exchanger in them, like on the left-hand side there. There's also central units that can use heat wheels. The problem I find with these is that the core, the exchangers or the wheels kind of tap out at efficiency. There's not really one of these out there that'll get to that 90% level that the heat cores will get to. So in these types of central ERVs, you're still going to need supplemental heating cooling, whereas on the 90% systems, you can sometimes get away. You can make the strategic decision to not do any supplementary heating or cooling. These types of systems are more complicated. They're more difficult to commission and maintain. They ultimately have a shorter lifespan especially because the core, the exchanger or the wheel, they're made of special materials that degrade. They just don't have the life that a metal core does comparatively. And something which didn't even make the slide here, but I should have put on there, both of these types of units require a defrost cycle. And a defrost cycle is just a waste of energy, right? Every so many minutes an hour in the wintertime, they have to stop recovering energy, go into defrost, typically using pure electricity to melt the ice off, in order for the system to continue to work. So, whereas with the core style units, because they're always switching, which you'll see in the next few slides, they don't require defrost ever. They just keep working in 60-second or 2-minute cycles. So there's a couple different, without naming any manufacturers specifically, there's a couple different styles of these units that I know are available in the Canadian market. This is certainly probably the most popular one. So this is basically, it's custom built, but it's an integrated system. You can see the 2 heat cores there, and then you can see there's basically 2 heat cores, 2 fans, and a damper setup. So in this simple example, there's not even any supplementary heating or cooling coil in there. It's just 2 cores, 2 fans, and dampers, which are switching every 1 to 3 minutes back and forth to charge one core and then use it, and then charge the other one while you're using the other one. So pretty simple. I mean, when it comes to mechanical equipment and ventilation equipment, it kind of doesn't get much simpler than this, especially when you consider that those cores, like I said, are just latticed metal blocks. There's no special materials there. There's nothing funny going on. All you got to do to these once every year or so, depending on your filtration, is just go power wash the metal cores and just get them cleaned off and make sure the dampers are working, obviously, and you're good to go. There is another style unit. I haven't seen as many of these, but again, it's still heat core based, still getting that 90% recovery. But you can see the biggest change in this style unit is the damper setup is much easier. Here you kind of had 4 independent dampers there that are actuating to change the airflow. Here you have one that just literally flips. So, but my understanding is these style units are a little more expensive. They're a little heavier. They take up a little bit more roof space. So there can be some pluses and minuses to that depending on the constraints of your project. But essentially the same technology, just slightly different setup to achieve the same thing. So takeaways, in-suite or centralized, let's throw out corridor ventilation. I mean, we're talking ERVs here. So in-suite or centralized are really your only two primary choices. The in-suite has been the go-to for code buildings up to this point, but it's going to challenge us from an efficiency and an air tightness perspective, which is why Passive House has kind of already stepped over that mark, because it has been the go-to design. And these heat core units are really the only ones that I know about achieving these 90% efficiencies with the simplest design. So, there are some downsides, obviously. Cost is a factor, weight is a factor. But if we're looking at this, from a performance perspective, from a certification perspective, getting 90% plus heat recovery is a large step to getting to where we need to be. Okay. So we talked about ERVs, but let's talk about the ductwork, because, as you saw in those diagrams, right, we're not just doing that one central shaft to the corridors anymore. We got sprawling ductwork out through the entire building that we have to deal with. That's part of these builds now. So, ductwork is made of a lot of different things. I mean, people think of it as normal, galvanized sheet metal, but, it can be aluminum, flex duct, fiberglass, PVC low profile. There's a lot of different things that are considered ductwork and can be used, legally as ductwork. And ductwork is just not, shafts. It's also components, isolators, takeoffs, fire dampers, turning vanes, plenums, all kinds of different bits and pieces that have to go together in order to create a working system. But what people don't realize, what a lot of mechanical engineers have never realized for years, is that ductwork leaks, and it leaks pretty badly in most buildings, traditionally. So, here's some facts from some smart third-party sources, right? Light commercial ductwork typically leaks 30% or more. That's out of the Florida Energy Center. I like that last one that I've highlighted. 75% of commercial duct systems leak between 10 to 25%. That's from ASHRAE. And if anybody knows ductwork, it's ASHRAE. They literally set all the standards for that. So we'll have them and SMAC now. But, between them, they know HVAC systems. And they literally say in their duct design manual that, hey, by the way, your ductwork's not going to be that good by the time the building's built. Just the way it's always been. And there's all kinds of trouble spots. I mean, complex joints, leaks, leaks on return, leaks on supply, leaks at the air handler plenums, like just all kinds of trouble spots on ductwork systems. And why has that been? Well, these are pictures of what ductwork leakage looks like. I mean, you can't actually see the air coming out of the ducts, but when you look at ductwork, and I encourage anybody who's working in a building, pop your head above the drop ceiling. You will find problems like this everywhere. And I'm not knocking sheet metal workers, right? This is, we really haven't changed the way that we've designed and constructed and sealed ductwork for decades, at least, and to be perfectly honest, I think our sealing is oftentimes getting a little bit worse, but I'll address that in a few slides. I mean, ultimately, when your ducts leak though, think about these passive house ventilation systems where I've got, the supply and exhaust running right next to each other, whether that's in the vertical shaft, whether that's in the ceiling of the hallway. If the supply's leaking, it's pushing air out. If the return trunk is leaking, it's pulling air in, and I'm essentially moving air around the building for no effective work. Right? Those two ductwork systems are sharing air. One's positively pressurized, one's negatively pressurized. I'm using too much fan, too much heating, too much cooling to move air around the building that is effectively doing no work because my ductwork is leaking. So the question is how do we fix this problem? Well, yeah, I love that picture. That's probably one of the worst ductwork joints I've ever seen in my life. But again, you will find that. I encourage you to go look for it. So the traditional way of sealing ductwork was mastic, tape, and caulking. Right? We just, the sheet metal workers, while they were doing their, the installation, they would just slather this on everywhere they could see, everywhere they thought it needed to be. And to my comment earlier about how this is getting worse, at least, in the 1960s, for example, we were still using oil-based mastics. Oil-based mastics are thicker, heavier, and they stay pliable much longer. But obviously, we've gotten out of oil-based products in buildings. We're now into water-based products. Water-based mastics are way worse than oil-based mastics. So this is actually a problem that's gotten worse over time as we've greened our building products. So I mean, you can tape, you can caulk, you can paint mastic on. This is how it's traditionally been done. But not all ductwork is easy to seal. You got to climb, or how are you going to seal the top of that ductwork against that cement? Against that cement floor plate. Like, difficult problem. So, what is the alternative? What can we do different today, and what can we specify into our projects to make sure this isn't an issue? Well, as I'm hoping many of you don't know, there is now aerosolized ductwork sealing technology. So this actually seals ductwork from the inside out, either in new construction or doing a retrofit. So it sounds like magic, but I'll tell you how it works. Essentially, this ductwork sealing equipment is attached to the system. The registers are blocked. So when you block the registers on a system, now when it's pressurized during the sealing process, all the air that's leaking out of the ductwork is coming out of the places you don't want it to leak out of, right? I blocked the registers, so all the air going in now is coming out of the cracks, the holes, the seams, and everywhere else. So once that's done, the sealant is injected, and it actually follows the leaky airflow and scabs over all the holes in the ductwork to create an almost perfectly tight ductwork system almost every single time in a matter of a couple hours. It really is quite impressive. So this is kind of what it looks like. This is more of a retrofit scenario in a school. But I'm sure that's how the equipment is set up. But what does it actually look like in the ducts? Well, there it is right there. So you can see the hole before, you can see the hole after. There's another picture of another seal there. Careful to note, this aerosolized ductwork sealant doesn't coat the inside of the duct. It doesn't leave a sticky residue everywhere. It actually only seals the holes because it only deposits out of the airstream where there's a pressure differential. So it leaves your ductwork in a really, really good state afterwards while sealing up all the leaks. So, what we're seeing now in new construction, and especially in passive house, which I'll show you some examples right after this, engineers now are just specifying the aerosolized ductwork sealing as part of a normal part of the construction. Now, they do this in two different ways, though. Either they say you will use this tech to seal the ductwork, or they'll just say the ductwork leakage of the whole building, the whole ERV system of the building, has to be 2% or less. Well, I guarantee you, using conventional sealing techniques in construction, there's no possible way to get 2% or less leakage on ductwork systems. It's not possible. It's even difficult to do that conventionally on welded stainless steel ductwork systems, which you don't see in residential buildings. They're only for laboratories. But even on those systems, they can leak oftentimes more than 2%. So this method of aerosolized sealing the ductwork to guarantee performance, it's been shown to be less expensive than trying to chase the leaks. And it's all computerized, so the process is guaranteed. You see the results in real time. And it can offer some interesting opportunities during the design to actually downsize the system, because most mechanical engineers don't realize that they're oversizing HVAC and ERV systems to compensate for ductwork leakage. It's kind of like buried in their assumptions that they, because it's always been that 10, 20% or more leakage. It's just kind of been buried in. But now when hey, wait, the ductwork's going to be 2% or less, I don't need any safety factor. I can really minimize out the safety factor on my air size, on my equipment size, my duct size, and ultimately my air delivery to the suites. So let's look at some examples. This is a building in Hamilton. I'm not 100% sure if it's on the tour tomorrow, but if not, I encourage you to drive by. It's a really cool looking building. So here's a case study for new construction. This is a 4-story MURB, social housing, library on the first floor, ventilated by 2 centralized ERV systems, both 1950 CFM apiece. It used that hallway ducted style design. And right from the specification phase, the design phase of this project, the target duct leakage rate was 2% or less. The contractor was under requirement to deliver that. And actually, the primary source of leakage, once the building was constructed and ready for sealing, ready for ductwork sealing, was the fire dampers. The fire dampers in this building were, I mean, I'm sure they're great fire dampers, but they were super leaky. And traditional sealants, mastic tape caulking, cannot be applied to fire dampers. It's not rated for use on fire dampers. So if that was all you had, you literally couldn't have fixed this problem. But thankfully, the aerosolized sealant is rated for fire dampers. So you can drive those leakage rates down. And I think you can see that in the table, right? All of the 4 parts of this system, supply return on both ERV systems, after the contractor had done as much as they possibly could for manual sealing, was still 50% leaky. Like, not even close. The aerosolized technology came in under 2%, all of them, target met, ready to go. And, you can kind of see, this is just one of the 4 graphs for that particular building, but you can see this is ERV2 return, started with over 1,000 CFM of leakage. And you can see the time base there on the bottom. So after about 160 minutes of the process going on, that's, the leakage rate was down to that under 2% leakage. 1,020 CFM down to 27 CFM of leakage. Done, verified, validated, ready to go. That ERV system is now going to work properly in that passive house from the moment you turn it on. But it's not just new construction. Here's an existing MURB. This is more traditionally ventilated. It's not ventilated to the suites. It's ventilated to the corridors, but it does have that central exhaust. So it's pulling air from the suites, dumping it back into the corridors. This building was built in the 1960s or so. So you can see, I apologize for the low-res picture, but it's the best I could get in this small little community in Manitoba. It does have just that one make-up air heat recovery unit on the roof that does everything. So it's drawing all the exhaust from the building. It's also supplying all the air to the building and then there's 4 branches off from that. So it was 4150 CFM. The impetus behind this project is that they're looking at deep carbon retrofits going ahead for this building. They're thinking about exterior panelization. They're thinking about a heat pump system for this building, right, which right now has boilers, but they first knew they had to get this ventilation problem under control. And when that ERV was installed around 2006 timeframe, they balanced, well, I shouldn't say they balanced it. They commissioned it by measuring the input and output airflow on the roof. But what they didn't do at the time was measure the airflow in each suite and in the corridors. And when they did that, it was terrible. A lot of the units, especially a lot of the units, were not getting any exhaust flow at all, even on this short building. So you can see the real life numbers from this retrofit scenario. All of the runs, the exhaust runs were much, much more leaky than the supply runs. The exhaust runs were 56 and 46% leakage. The supply runs 27 and 14. With this technology, all brought under 4%, which is really, really good for a retrofit. And ultimately, in the end, this building balanced out perfectly. Every suite had exactly 50 CFM of exhaust. The corridors, every corridor had the right amount of air coming out of the grills. The building is now in a good state to kind of take that next step down their energy efficiency journey. So again, some examples of that. You can see the leakage there. Driving down, these seals were, one was about 120 minutes, one was about 70 minutes. But again, just, inject, aerosolize, let the sealant find the holes, seal the holes up, get out of the building, and done. So just some takeaways on this section here before I close it out. Ductwork leakage is a real problem, and it's a real problem in existing buildings. It's going to be a real problem in any new construction passive house building. Specify tight ductwork. It'll just make your life so much easier in the end when it comes to actually commissioning and getting the building going and optimizing the design. The traditional sealing techniques, I hope you understand now, they're just not reliable. And something like this can produce much, much quicker, verifiable, reproducible results that are just going to end up making your building even better. So just a couple future things before I open the floor for questions. Just a few things I have in my mind, one of which I'm definitely seeing some application on now, but is solar air preheating. So I have a saying that I bounce around once in a while, but all of the sunlight hitting your building and property is yours to use or to waste. So in the argument of this case, where you got a mechanical room on the roof, which is fairly common in a lot of MURBs, all that sun that's hitting the mechanical room, unless you've got solar panels on the side of that, which we traditionally don't do because they'd be really inefficient, it's a great place for a solar air preheater. Right? Let's just use that space. It doesn't necessarily change the building design. You would have had to have clad that mechanical room anyways. So if we do need a little bit of heating boost, in the summertime, this is going to have no impact. You're going to bypass that with a damper. But at least in the wintertime, you can use some of that sunlight that would otherwise just go to waste hitting that mechanical room on the roof. Pretty cheap upgrade. Not something you're probably ever going to do in retrofit because the benefit to cost is pretty low. But in new construction, again, you would have had to clad that room anyways. So, and another interesting thing I came across, I've not actually seen this, but I kind of, spurred some interest in me. You might have heard before about like naturally ventilated buildings ventilated with chimneys, using the stack effect. Certainly there are some examples here, even in the Toronto area. York University's got a building that's got a big natural chimney on it. So that's like 3 stories higher than the rest of the building in order to create this effect. I'm not 100% sure if this will ever be possible in the passive house world, but it's something to think about. If we can use nature and physics in a way that requires less fan energy input. I think it's certainly something to think about. You can kind of also get a sense here how they're pulling cold air from the bottom. I have seen that done, for example, in a school in Ontario where they actually pre-cool their outdoor air for air conditioning through ground tubes. So they actually pull the air from the yard under the ground in ground tubes before they bring it into their ventilation system and cool it to air condition the building. And they actually get a little bit of cooling out of the ground. So it's kind of like free air cooling out of the ground, but something to think about because, it's tough. We have such wide temperature ranges and humidity levels that I don't know if this will ever be possible in Canada, but it's something to consider. So final thoughts, definitely indoor air quality has to be considered a core design element of any building we do these days, right? COVID has reawakened us to that fact. And by the way, don't trust your senses, as human senses to detect bad indoor air quality. We can't do that. So, we often get caught in what I call the IAQ trap. If you walk into a building and the temperature's good and you don't smell anything, you assume the indoor air quality is good, and nothing could be further from the truth. Heat recovery is obviously a core part of the design. Central ERV systems is kind of where the passive house world is at, and I think they're going to stay. Ductwork leakage, historically been a real problem, but we can now address that pretty easily. And, we always do need to be innovative, right? We do need collaborative design, integrated design in order to deliver these projects at the, highest performance, lowest cost, and thinking about these kind of things right from the beginning. Okay.